This presentation will cover the concept of algebraic complexity, focusing on the complexity of algebraic computations and decision trees. We will explore how these concepts apply in mathematical computation. Algebraic complexity is the study of computational resources required to perform algebraic operations and solve algebraic problems. It primarily focuses on addition, multiplication, and division operations over fields. There are two primary models for algebraic computation. The first is straight-line programs, which consist of a sequence of arithmetic operations without any branching. The allowed operations are addition, subtraction, multiplication, and division. The second model is decision trees, which involve branching computations based on the results of comparisons. Here the operations include less than, equal to, and greater than. A straight-line program is defined as a sequence of arithmetic operations performed in a fixed order, without any conditional branching. For example, consider the following program. First, x1 is assigned the sum of a and b. Second, x2 is assigned the product of x1 and c. Third, x3 is assigned the difference between x2 and d. Finally, the output is x3. A decision tree is a computational model where each internal node performs a comparison, and the computation branches based on the result. For example, at a node, we might compare x and y, branching to one path if x is less than y, and to another path if x is not less than y. We can measure the complexity of algebraic computations using two primary measures. First, time complexity denoted as capital T of n, which counts the number of arithmetic operations required. Second, space complexity denoted as capital S of n, which measures the amount of memory needed for the computation. A classical example in algebraic complexity is matrix multiplication. Using the standard algorithm, which involves a triple-nested loop approach to multiply 2n by n matrices, the complexity is on the order of n cubed. A lower bound is the minimum number of operations required to solve any problem within a given class of problems. Common techniques for determining lower bounds include adversary arguments, algebraic methods, and information theory. The height of a decision tree represents the worst-case number of comparisons needed to reach a decision. The lower bound for the height of a decision tree is ceiling of log base 2 of n factorial. Algebraic complexity has key applications in polynomial evaluation, sorting algorithms, optimization problems, and cryptographic systems. It provides fundamental limits on computational efficiency and guides the design of algorithms. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.